ray tracing in Unreal Engine 4.22. To introduce myself, I'm Marcus Wassmer, the Engineering Director for Graphics here at UE4. You can kind of see me behind the computer here. Stand up and wave. And let's look at a quick overview here. So first we want to talk about how we've implemented ray tracing in UE4 over the last year. We're going to take a look at how the movie Troll was made, which we did to kind of show off the new tech. I'll be explaining the goals of the movie and some of the challenges we faced and how we approached them. And then we'll do a breakdown on the content and art pipeline, explain how ray tracing helped the art team at our partner company. And then finally, we'll do some in-depth technical review of some of the code and rendering techniques. So first, let's give a little background on what we've been doing on ray tracing for the last 18 months or so. As some of you may remember, last year at GDC, we presented the Star Wars movie Reflections in collaboration with NVIDIA and ILM Lab. And the goal of that project was to show real-time ray tracing in UE4 for the first time. So this ended up as a pretty good demo, but wasn't really the final place where we wanted to be, but was in fact just the beginning. A few months later at SIGGRAPH last year, also in collaboration with NVIDIA and Porsche, we presented the movie and interactive demo The Speed of Light, where we showed off more complex ray tracing effects on slightly newer hardware. And then with all the lessons that we learned over the course of doing those demos and prototypes, we actually rewrote all the ray tracing code from scratch, just to make sure that it was ready not just for demos, but ready to be a part of the engine for real for everyone. So to showcase it, we've made the new cinematic Troll, and let's take a quick look. Okay, so that was the cinematic. And the goal of Troll was not just to showcase ray tracing by itself, because we kind of did that last year. We kind of had two aims. One goal was to explore just how far real-time digital content creation could go by creating a high-end cinematic piece, and how we could mix ray tracing with other key elements of our game engine, like Niagara Particles, Alembic pipeline caches, sequencer tools, and of course, digital humans. So all of those components have been vastly improved thanks to this demo. And our second goal was to make this tech accessible to anyone, as opposed to last year's demo, which was prototype code that was Epic internal only, that no one else had access to. Instead, this year, the movie was made by our partner, Goodbye Kansas, using basically the UE 4.22 code that is available to everyone right now. So There's no more secret sauce, just fully integrated code in the engine that anyone can use. So let's take a look at some quick data, doing some comparisons with last year's demos. Troll is an order of magnitude more complex than our previous demos in almost every respect. It's got more polygons, more complex lighting, and more elements of the engine all interacting together. And you can see some of the stats there on the slides. But the render time is the same. Both current and previous demos were all running at 24 FPS, which means that complexity has grown a lot while maintaining the same rendering times, which means that performance has been massively improved. So the tech and the hardware is much, much faster this year than it was last year. And speaking about hardware, let's talk a little bit. The Reflections demo was done with an NVIDIA DGX station that had 4 Tesla V100 GPUs running in a multi-GPU sequence. This machine cost somewhere between $50,000 and $70,000 US. This year it took 2 of them, but no. So this year it was really important to us to make sure that we could run it on a single consumer grade card, and we succeeded. It's running on a single 2080 Ti. So one of the goals of the demo to be accessible tech doesn't just mean that everyone has the code available, but that the cost is within reach for regular game developers. So you don't need a $50,000 box anymore. A 2080 Ti will take you a long way. And also kudos to NVIDIA for doing such an outstanding job of improving their hardware in just 1 year. So let's talk about the technical challenges of Troll. There were 2 main ones, mainly performance and digital humans. And let's kind of focus on performance first. So during development, we're always doing performance testing. And we end up with performance charts that look like this. And this was our performance chart from a few months before GDC, where you can see that the dotted line is the kind of frame budget for reaching 24 hertz. And you can see that basically the entire demo is drastically over budget with lots of spikes on frame boundaries and such. So what do we have to do about this? There were quite a few things involved, but we don't have time to talk about everything. So we're going to talk about the main major 3 components that got us back under our performance budget. First is a shift in the renderer from an immediate to a retained mode. The new ray tracing implementation was built on top of a complete refactoring of the rendering mesh pipeline. Tomorrow, I'll be giving a full-length talk about this pipeline, but for today, I think we can say that the most important change here was to take work that was being done for every draw, every frame, and to move it for when draws were added to the scene rather than every frame. This is important for ray tracing because ray tracing can access any part of the scene, which means you can't use frustum culling or occlusion culling to remove work. You have to prepare the entire scene. So moving work out of every frame was very important for performance. And please come tomorrow if you would like more details on that. Secondly, let's talk about ray navigation, which we'll cover a few slides here. So first, the general performance of a couple of different techniques. We found that shadows and AO were actually pretty affordable. We were quite surprised to find that in some use cases, ray trace shadows were actually faster than raster shadows. And these are probably going to be the first uses that you'll see in games, would be my guess. But things are different with other effects like reflections or GI or translucency. These are actually quite expensive and kind of force us to use different strategies to keep performance in good shape. Of course, I should note that for all these techniques, denoising is critical because rays are so expensive no matter what. We can only afford a few rays per pixel, which means denoising is super important for any type of ray tracing, real-time ray tracing effect right now. So, one of the main strategies involved are tracing rays only when they're needed, and then falling back to like traditional mechanisms when you don't need the rays. So let's take a look at an example. So the fundamental idea here is that you don't need to trace rays to calculate reflections when roughness is very high. So if you look at the image, you can see that we need rays to compute accurate reflections in the water, which is very smooth. And it can also, calculate proper distortion for the water ripples. However, in other parts of the scene, like the rocks, you don't need to trace reflection rays because they're largely diffuse surfaces, and you can just light them with traditional rasterized techniques, and it looks very good without the ray tracing. So yeah, since rays are super expensive, the most obvious way to make things faster is to just not cast rays. The second thing that is, perhaps obvious but surprisingly useful is to trace short rays whenever possible. So for example here, if you're computing, say, the ray traced AO on the princess's face, you don't really need the rays to go from her face all the way out into the forest and bounce around all the trees. Like a very short ray picks up the occlusion that you need, and this cuts down on the traversal cost pretty significantly. There are other techniques to optimize ray tracing. For example, there are ray flags you can set to, force intersections to be opaque, or, just remove things from the ray tracing scene that you don't need them to cast shadows or reflections. Really, just check out the 4.22 doxing code for more details on those things. And finally, let's talk about Niagara Particles. So Niagara played a pretty fundamental role in this demo. All the fairies that you saw were skeletal meshes that were spawning lots of Niagara particles out of them. In fact, in many shots, we have more than 500,000 Niagara particles running in real time. And these need to be visible in ray tracing effects like reflections because they're a key part of the scene and they need to be in the water. This means that they had to be part of the BVH that's used for ray tracing. And these particles have a lot of motion, which means we couldn't use like a cheap refit on the BVH. We had to actually rebuild it every frame, which was too expensive. So we had to do, a little bit of a cheat. So what we did in this case was actually reduce the number of particles that were in the ray tracing BVH to about 1/3 of the total, and then compensate for the lack of particles by increasing their brightness, by the same relative to amount. So it turns out that this is a pretty simple idea, but actually works really well. You can still see all the richness of the particles in primary visibility, and in the reflections, you get a good enough of a look that you don't really notice that 2/3 of the particles are gone just because of how many are already there. Okay, so let's have another look at performance. So this is the original chart. This was actually done on a more powerful card. This was on a Quadro RTX 6000. And then finally, at the very end, after we applied all those optimization techniques, this is kind of what we get on a 2080 Ti. So now we're running at 24 hertz with no hitches. And in fact, there's you can see on a lot of this, there's a little bit of overhead left that we just didn't tell the art department about. So this, we didn't want them to get too crazy. Okay, so another challenge of the demo was to get a realistic digital human on the screen. Fortunately, 3 lateral is now part of the Epic family, and helped us out with really high quality digital human work. Digital humans is on itself a really complicated complex topic that probably needs its own talk. So I'll just say that lighting a digital human using ray tracing is much easier for a traditional lighting artist. The ability to use area lights with soft shadows helps them get a more realistic look. And also during the demo, we had an artist request for analytic barn doors. You can kind of see on the picture, it's the little flaps on those lights like they would have on a film set. So those are part of 4.22 now. And this is just another example of how, when we do these demos, we kind of end up implementing features that helps UE4 get better for everyone. And speaking of the art team, I would like to talk a little bit about our partner on this project, Goodbye Kansas. So Goodbye Kansas is a visual effects studio that works on game trailers, cinematics, feature films, TV shows, advertising. They're based in Stockholm in Sweden, and they actually have a gaming background, so it made a lot of sense for us to partner with them. So for Goodbye Kansas, they've been waiting a long time for ray tracing in a game engine, because now they can finally use lighting concepts that they're used to in traditional offline rendering and use them in real time. They get correct reflections, which is an improvement over SSR and planar. They get much better glass and liquids with translucency, ray trace translucency. Area lights gives them more natural looks for environments and for characters. And with real-time GI, they don't have to rely on light bakes, which means they can see results in real time when they're doing their lighting. So let's take a look at a quick demonstration video here of a still from the scene. You can see how a lighting artist might adjust the size of an area light here to get softer shadows where they would like. And we can see, the result of the subtle, I don't know if you can see it on the projector there, it's very dark, maybe, but if you change the roughness on the crown here, you can see that the lighting from the reflections of the princess and the crown actually subtly contribute to the lighting in a realistic way there. We kind of toggle the roughness to make that obvious. And I think as the camera pulls out, well, there are places there where you can see the accurate reflections off of the ripples there that you wouldn't get with a normal screen space reflection. So in addition to that, with ray trace translucency, they can get physically correct absorption and refraction, like in the water in this shot where Bianca is looking down through the water. So, being a traditional VFX house, Goodbye Kansas needed to fit Unreal into their VFX pipeline. So to help their artists work more efficiently with tools like they're used to, they created some of their own in Unreal. So with the material editor and blueprints, they were able to customize the engine to their specific needs and introduce more classic visual effects pipeline workflows into the engine. So this lets them kind of lower the bar for entry for artists that are new to a game engine, but still maintain the quality control they need for high-end visual effects. Also, they were able to make use of the Python support in the engine so that they can extend their normal pipeline to support Unreal like any other application that they have. So kind of specifically what they did, one thing, they created an Uber shader for their artists so they don't have to learn the material graph. So this saves a lot of time and troubleshooting. With an Uber shader like this and some material instance parameters, they can simplify things for the kind of the new artists. They also implemented UDIM support so they can use VFX assets directly from their pipeline. This support is just a material function that they made in the material editor and put in the Uber shader. another thing that was helpful for them was to make kind of a light rig environment to do look dev. So with ray tracing now, they can get a more accurate representation of lighting conditions and get closer to a one-to-one match on what they would expect from an offline renderer. Their light rig also has runtime controls, so they can kind of pack this thing up and use it for daily content review, or even send it off to a client to review assets interactively. Another thing that Goodbye Kansas was able to use effectively was Alembic caches. So these got major improvements in 4.22. In fact, large Alembic caches are something like an order of magnitude faster now. For this project, the dress was actually simulated in Houdini, but imported as an Alembic cache for each shot. So this is a pretty big feature for your traditional VFX studios. So the overall takeaways here are that they now have a robust tool set for creating cinematics in real time, and this gives them a much faster way of creating content. Because they can make changes more rapidly in real time, this means they can change the way they think about production planning, or instead of a very long linear process, they can make tweaks up until the very end more easily and do more things in parallel. All right, so let's move on to some of the more technical bits here. First, I want to talk about the programming RHI layer that we use to kind of abstract away the DXR interface in Unreal Engine. So kind of the bulk of the work still lies inside the D3012 layer, but we do expose a thin abstraction. And at this level, we kind of expose the major concepts for ray tracing. Geometries, scenes, shaders, and pipeline states. Let's take a look at each one here briefly. So this is a ray tracing geometry, and this just contains an arrangement of vertex positions and indices. It's basically a mesh. And embedded here is we also have the concept of geometry segments, where a segment is just a subrange of, the verts and indices. But this contract just kind of allows us to bind a different material to different parts of the same mesh. It's very similar to static mesh sections in the raster pipeline. So there's also layered on top of that, there's the ray tracing geometry instance, where this is just a reference to the geometry combined with a transform. So this is kind of the natural abstraction to instance multiple copies of the same object throughout the world. Along with the transform, there's also some user data here that can be used for custom purposes in shaders. And there's also an instance mask that can be used for visibility within ray traversal. And then that can be different per instance. Next, there's a ray tracing scene. And the ray tracing scene is just simply a collection of the instances. That's a fairly simple concept. And then, so let's talk about the different shader types as well that we expose. So in 4.22, we support from DXR the closest hit shader, the any hit shader, the miss shader, and the ray generation shader. So notable omissions to this are 4.22 does not ship with support for intersection shaders or callable shaders. However, I think 2 weeks ago, we checked in support for both of these into dev renderings, so support for both those shader types should be in 4.23. So in the process of using these, we end up associating closest hit and any hit shaders as belonging to geometry groups, while miss and ray generation shaders typically belong to a specific pass or rendering technique like reflections or shadows. And of course, resource bindings for all the hit group shaders needs to be identical, but UE4 uses automatic resource binding and reflection to maintain that property for you. And then there is the ray tracing pipeline state. So the pipeline state for ray tracing aggregates ray generation shaders, mist shaders, and hit groups into one big collection for execution. The ray trace PSO must contain at least one ray generation, closest hit, and mist shader. We kind of create one RT PSO that contains all ray generation shaders required for the current frame. It also includes all material hit shaders that are currently loaded. And then there's a kind of a trivial mist shader for ray tracing effects. We actually rely on mist behavior to be handled by the ray generation shader, not by the mist shader. And then finally, if you're familiar with DXR, you might be familiar with the concept of the shader binding table. So where the PSO kind of maintains the list of shaders, the shader binding table contains the list of all the resources, like textures and buffer reads for all objects for the whole scene. We don't expose the shader binding table directly to code, but instead we kind of use a convenience function here, the set ray tracing hit group. And this is what you use to bind a particular geometry segment and its materials into the shader binding table. We might expose the binding table to be explicitly managed by the high-level code later, but we're kind of waiting to see what other APIs might do with ray tracing before making that decision. Okay, so let's kind of look at what happens in a frame and some geometry considerations. So at the beginning of a frame, we kind of have to gather all the geometry instances to assemble them into the ray tracing scene. We reuse previously cached static data, and we build new dynamic data. We also have exposed a new virtual function to extend implementations for dynamic geometry in the future, which we'll talk about in a minute. So after assembling all the instances, we have to apply updates. So this means updating vertex positions for like skeletal meshes or Niagara particles, and rebuilding any acceleration structures that we need. Once the individual bottom level or object level acceleration structures have been updated, then we have to rebuild the scene acceleration structure. Finally, we gather ray generation shaders and then bind them to the ray tracing pipeline. Even though we're ray tracing, we still have to render the normal deferred rendering base pass to prime the G buffer, because the G buffer data is still very important to all the ray tracing effects. And we still do traditional rasterized lighting on large portions of the frame. So then finally, once we have all that data, then we can start running the different ray tracing render passes. So I kind of briefly mentioned supported geometry before. We'll list them here. Ray tracing right now in 422 only supports static meshes, skeletal meshes, geometry caches, which is kind of the internal name for limbic caches, and Niagara particles. Other geometry types, like landscape, for example, will be added in later versions of the engine. Yeah, so this is the kind of function for extending that geometry support. If you were making modifications to the engine and wanted to make a new geometric type that supported ray tracing, you would just need to fill out this function, which needs to create your ray tracing geometries, create your ray tracing instances, define your material bindings for each geometry segment. And if you want an example of this, just take a look at the Niagara renderer sprites. This is one that we implemented, and you can kind of look at it for a good example on how to extend things yourself. So also, when we were kind of designing the code, we had a few choices to make here in the mesh pipeline. So first, when building acceleration structures, you have a choice as to whether to refit or rebuild them. Where a refit is faster but gives kind of a worse result, but a rebuild is a little slower but gives a tighter result. So currently we choose to always rebuild our bottom level acceleration structures when their data changes, just for ray traversal speed in the end. Also, when it comes to level of detail, or LOD, only static meshes in 422 support LOD, and dynamic meshes currently do not. And then finally, it was very important for us to set a flag on geometry for visibility and shadows. So you can prevent geometry from becoming occluders for ray trace shadows if you need to for performance or artistic purposes. And this was kind of required to keep the demo in budget. Okay, so now let's talk about some of the specific ray tracing techniques, such as shadows. So for ray tracing, you kind of compute a shadow visibility mask in a similar way as the rasterizer. The ray tracing visibility masks are just straight drop-in replacements for a traditional shadow map. They basically look the same. The difference is that with ray tracing, you can kind of accurately calculate visibility for an area source, which is kind of an unsolved problem in rasterization. And we support a number of different light types for ray trace shadows, specifically directional lights, point lights, spotlights, and rectangular lights. Yeah. And again, because we can calculate visibility for an area source, we also support, as I mentioned, rectangular area lights, but also spherical area lights. And for directional lights, we support a directional disk light, which kind of emulates the sun. All right, so let's take a look at kind of the raw output from ray tracing shadow calculation. Again, because tracing rays is still very expensive, usually we can only afford about one sample per pixel, even on shadows. And this is kind of the result that you get from a single sample. It's pretty ugly. However, if you apply a smart denoiser, it turns out you can get a very smooth result. And this is kind of the fundamental thing that makes real-time ray tracing viable. Even if you do something like go from 1 to 64 samples per pixel, you can see that even at 64 samples per pixel, the image here is kind of grainy. Another key thing to notice is that if we flip between the denoised version and the high sample count version, we can see that the denoiser does a pretty good job of approximating the real result, or the closer to real result, of the 64 sample per pixel version. So, one last time. So the next effect that was used in Troll was ray-traced ambient occlusion. So this one is a similar drop-in replacement for screen space ambient occlusion. Kind of the texture mask you get looks basically the same. The ray generation shader for ambient occlusion will kind of fire rays with a cosine weighted distribution, based on the normal and depth information in the G buffer, and then it'll record the hit and miss ratio. And one of the the advantage of doing it with ray tracing is that you can you have information from the scene that you wouldn't get with just screen space data. So if we take a look at an example, this is a kind of an interior scene. This is the screen space AO version, where you get the kind of fairly typical short range AO along the geometric intersections and corners of things. But with ray tracing, you get much more broad AO that kind of more matches reality. You can see this image has not been denoised. It's still a low sample count. And finally, I want to mention that to correctly denoise both shadows and AO, we need more than just whether a ray hit something or not. We actually want to know how far the distance was to the nearest occluder. Because with this, you can do a better estimation of penumbra size for shadows, or the intensity of the AO calculation. And to get this means that both AO and shadow ray generation shaders need to cast rays that use a closest hit shader. So this incurs a little bit of extra cost, but we believe that the quality difference is worth the cost. All right, so now we're going to transition to talking about techniques that require material support to actually evaluate the materials. So these ray generation shaders actually use the shader binding table, which binds the geometry segments to the custom hit groups, which have the material bindings that was made earlier. So, for example, Reflections has a unique ray generation shader. The integration of the reflection term, we start at the G buffer. And rays are cast according to a distribution that is proportional to the GGX lobe defined by the material. So this is different than AO, which uses the cosine weighted distribution. So if the ray hits a surface, then we have to perform full material evaluation and full direct lighting calculation on the surface to get the proper reflected result. So we also have to be very careful when we implement the ray tracing code to make sure that it's running the same lighting calculations as any other lighting in the engine so that the results match. And of course, the advantage of Raytrace Reflections is that it can capture phenomenon that the screen space reflections can't. Obviously they can reflect things that aren't on the screen, for example. So just here's a quick image of one of the shots from the movie with screen space reflections. You can see the kind of weird warping of the fairies and kind of missing detail in the crown there. But with the ray trace reflections, now we suddenly get the full detail in the water like you would expect. And you'll also get proper distortion from any ripples in the water that you wouldn't really get from a planar reflection trying to emulate the same thing. Another powerful mechanism of ray traced reflections is that you can evaluate multiple bounces for your reflections to get complex interreflections. So as you might expect, the more bounces you have, the more costly it becomes. So typically in our real-time demos, we limit the bounces to 1 or 2. But for a cutscene or for a marketing shot, you might want to crank that up for quality, depending on how shiny your scene is. Translucency works a little bit differently from reflections. So instead of looking at the surface to decide where to cast rays, we actually just trace rays between the camera and the G buffer. And then when hitting a translucent polygon, we can trace a new translucent ray in the refracted direction and then perform direct lighting when we finally hit the surface. So, we can choose what to do when we hit refractive surfaces for performance. So for example, when you hit a refractive surface, what you want to do is use the specular component to determine the index of refraction and determine if you really need to bend the ray. This is a performance concern because casting extra refraction rays costs extra performance, and as we know, not tracing rays is the fastest way to do ray tracing. So, something that's not refractive, just your single ray goes straight through, and it's much cheaper. But you do it when you have to. All right, so next thing we're going to talk about is some kind of experimental features that we did. These features I'm going to talk about are kind of not production ready in 4.22, but they have some interesting results that are worth talking about. So first, I want to mention that the sampling for these techniques is based on hierarchical sample warping. And you can see that it's fairly complicated. So really, I want to refer you to the authors here on their wavelet importance sampling paper. And there's also a very good example in Ray Tracing Gems, Chapter 16, that's got an excellent description of this method that you guys should check out. So this is just for reference. Go have a look at it. After the talk. So the first thing that we looked at doing was a textured area light integrator. And kind of the way this works is that when we load up the light and the texture, we build a bitmap of luminance. And then for ray generation, we use the hierarchical sample warping to do importance sampling on the textured area light so that we fire the rays where they need to go. And because it's a texture, what this allows us to do is have colored shadows, as you can see in the image. And that's kind of the main advantage of the technique over the standard rect light that's in the engine. Another experiment that we wanted to do was to light a scene with just the skylight, no directional lights. So in this case, we similarly build a bitmap of luminance from the skylight cube map. We also cache the PDF, or probability distribution function, and solid angle per cube map texel. And then for ray generation, we kind of split the integral to only handle the diffuse part, because we don't really need to calculate specular lighting for the purposes of this skylight. And then you can see here that with this method, there isn't actually a directional light in this scene. The long directional shadows are just coming from the disk of the sun that's in the cube map, which is really the result we were going for. This is convenient for artists if they can light a whole scene with just one cube map. But this is missing a little something. You can see the shadows are a little bit too dark. So we also wanted to try our hand at global illumination. So global illumination, similar to AO, kind of casts according to a cosine weighted distribution. And in this experiment, we were performing next event estimation, which is like a stochastic application of direct lighting to limit computation. This is a technique that's often used in offline renderers. In our case, for this experiment, we did find that it converged to a path tracing result with enough samples. So it was a successful experiment, but kind of too slow to put into the engine at the moment. And then lastly, we wanted to experiment with image-based lighting. So this is a technique that's often used in the VFX industry for film. What'll happen is someone will be on a film set filming actors. You'll go and take a 360-degree camera and take a capture of the film set so that you can get a capture of the lighting. And then with the cube map that's generated from that camera capture, when you go later to composite CG effects into your scene, you can relight them so they look like they fit into the scene based on the lighting that was actually captured on the physical set. So to try things out, we wanted to start with kind of a bigger landscape. So our friends at Quixel were kind enough to let us borrow their landscape. They had done for a short film piece that they showed off at GDC this year. And here you can see, kind of what it looks like just with traditional rasterization. This scene has about 70 million triangles and about 1,000 draw calls in it. And it looks pretty good just for rasterization. So if we swap over to our ray tracing techniques, this is just with kind of the standard engine directional light and RTAO. You can see that the AO distance is quite large in comparison to the SSAO render. And it's a pretty good approximation to the direct lighting term. But for IBL, you really need the cube map data. So we want to see what it looks like with our experimental skylight integrator. So in this image, we've completely replaced the previous lighting with just the skylight, i.e. there's no directional light in this scene anymore. We also added the global illumination in to provide one bounce of indirect lighting. You may notice that the windows and the glass don't look quite right, and that's because we're missing the skylight contribution from the reflection pass here, but didn't quite have time to fix the image. So this is not denoised. We've got 16 samples per pixel on the skylight and 10 samples per pixel on the global illumination, and it's kind of running at 24 FPS. If we crank that up to get rid of some of the noise to like 128 samples per pixel on the skylight, we drop us down to, just really slow 1 FPS, but we can get an idea of what it would look like if we had a production-ready denoiser to keep us up at the higher frame rate. And the reason why we want to do this for ray tracing, for one, is ray tracing can be dynamic, which means we could potentially scroll the cube map to kind of emulate time of day and not have to bake any lighting. And we actually did that and have a short demonstration video to see here. So let's take a look at that. So here you can see the shadows, no directional light here. This is completely lit just from the cube map, and the sun's gonna kind of slowly hit set here, and the shadows will creep across. So this image is doing the very slow 128 samples per pixel. This one is not running in real time, but we expect we should be able to run it in real time with denoisers sometime this year. All right. And then kind of the last major feature that we added for 422 is a reference path tracer in the engine. So this is an unbiased path tracer that's meant to be used as a ground truth. It's designed mainly as a reference for graphics engineers. So if you're doing a new approximation, you don't have to export your scene into an external offline renderer like Mitsuba or something to confirm that you've got it right. You can now do it directly inside the engine. And we expect this to be a foundation for future techniques like RTGI or upcoming changes to light map baking. All right, let's take a look at, before we finish the talk, I want to talk about the future a little bit. We think that we currently have a pretty good feature set, although it is in early access. Our top priority right now is performance and stability. So mainly look for stability and performance improvements in 4.23 rather than feature work. But we're also working on other things like, intersection shader support, adding new geometry support, constantly working on improvements to denoisers and the path tracer. And we're planning to also work on like an interactive GPU light map baker directly in the editor, and also adding multi-GPU RHI support for ray tracing. So I'd like to thank our development team. They did a hell of a lot of work in the last year, and we couldn't have done it without any one of these guys. There's a lot of other people we'd like to thank, but the slides are only so long. And yeah, so UE422 contains ray tracing. It's early access. We think you can get really awesome results with it, and we can't wait to see what you guys are going to do with it. All right. Thank you very much.